Good morning, friends. So today we are going to talk about the eccentric connection, which is there are two varieties of eccentric connections. One is the out of plane, the second one is a in plane connection. So in these two, the out of plane is the connection where suppose I have an I section to the end of the flange, so I will connect a plate with help of weld. That weld could be butt weld or fillet weld. So this will be my web, this will be my flange. There will be a flange. So this is the I section where the plate is welded either by butt or by fillet. Suppose there is a load of P. This is out of plane bracket. Similarly, there is a in plane bracket where now if you look at carefully, now my flange is here and my plate is something like this. So now I am welding to the flange in the plane of the flange. So this plate and this flange of the plate I section are in plane, same plane. So let us say this is the road P. Now the welding is done along the plate which is the shape of C. In this case it is only vertical. So this is called out of plane, this is called in plane. In order to explain this properly, so let us see a model with the help of a cardboard. Let us say this is an I section. If you look at the I section here, so this is a web portion, this is a flange portion, and this is another flange. Now a bracket plate is to be welded, and I am going to weld directly to the flange. And if you look at the plane of the flange and the plane of this plate, these two are perpendicular to each other. So this is, now if you carefully observe what happens is that due to this load which is coming through my pencil, one, due to the vertical load, the welding subjected to shear the downward, and secondly due to the eccentric distance, that may be the tension at the edges and compression at the edge due to bending. The other connection is the in plane connection where I can see is something like this. Here this is a load and the plate is connected to the flange. Now the flange plane and the plate plane is same. That's why we call it as in plane. Now due to this load, one possibility that the plate may get a shear off. That's why we call it as shear stress in the welding. Second one, due to this load, there may be twisting may happen. Twisting. So we call it as the stress due to twisting moment. So we need to work out the stress, the resultant stress at the extreme weld because of the shear which is vertical and due to the twisting phenomena. Right? In case of the in case of out of plane, so one is a shear, second is the bending. So resultant stress at the top and bottom will be your bending and shear. So this is what we have to find out. So if you look at carefully at the in plane, so this is the C-shape welding, the width is B, depth is D, then we may have to find out the centroid of this weld group with the shape of C, and this extreme point will be subjected to a twisting stress, which is a shear stress due to twisting and the shear stress. So from the CG, the distance we call it as R max, and because this subjected to twisting, so we have to find out the IZZ, which is polar moment of inertia. Polar moment of inertia divided by extreme distance will give me the suction modulus. Then the moment P into E will give the moment P into E by suction modulus, polar suction modulus, IZ by R max will give me the total stress, which is the stress due to the twisting. So let us explain this. How do you solve the problem of design of this bracket, outer plane bracket, and design of in plane bracket? And quickly want to explain what is the design procedure of the outer plane bracket and in plane bracket. So if you look at, I already mentioned to you the outer plane bracket, the welding could be the butt weld or welding could be a fillet weld. But whereas in in-plane bracket, it is fillet weld is only possible. This is butt weld or fillet weld, both options are there, but in case of in-plane, only fillet weld is possible. So as I mentioned to you, so there will be a direct shear stress which is equal to, so let me explain first about the butt weld. Shear stress equal to P by D into TE. And I can draw you a small diagram of this. This is the P and this distance is eccentricity E, and this is the weld I am going to do here. I call distance as D. This is direct shear stress. T is the effective throat thickness, D is the depth of the bracket, and P is the load applied. And due to this eccentricity, there will be a bending stress which is equal to M by Z, which is equal to P into E by T into D square by 6. Now, if you look at the top point or the bottom point subjected to both the stresses, extreme, so we have to take a resultant stress, also called equivalent stress. So we say this is to be a Q, this is to be FB. The resultant stress or the resultant stress is FE is equal to your FB square plus 3 times Q square, and this resultant stress must be less than or equal to Fy by gamma m naught. That's all. Now depends upon whatever asked. If load is asked, you can find out the depth. If depth is given, I can find out the load. Simply the equivalent stress has to be equivalent to Fy by gamma m naught. I can find out the design capacity of the outer plane bracket if it is butt weld. Now what happens if this particular welding is not a butt but it is fillet weld? The only difference will be the length. If you look at carefully from this side, this is a flange, so I will have to see two different welds, two lengths of weld I can see, whereas in the butt weld I can see only single weld. So that's why the direct stress, which is direct shear stress Q, is equal to the P by 2 into LW, because two lengths are there here. LW, length of the weld 1 and 2, and into TE, effective throat thickness. The bending stress FB is equal to again M by Z, which is equal to P into E by TE into LW square by 3, and the resultant stress FE is equal to square root of FB square plus Q square, and this must be less than or equal to FU by root 3 gamma MW. That's all. So this is the direct shear stress, this is the bending stress, and this is the equivalent stress at this top point or bottom point. So the resultant stress is this, and this has to be less than or equal to the ultimate stress by root 3 gamma MW. If equal, we will be able to find out the P or the length of the weld or size of the weld, whatever necessary. Now whereas coming to the in plane, now I have a plate and the flange plate both in the same plane. That's why I call it as in plane, where the welding is in the form of C. Right? Now again, due to this load, as I told you, that's one could be a shear, second is your twist. Both stresses will happen. So then I may have to find out the CG, and this distance is my eccentricity from the load up to the CG of the weld. So the direct shear stress, which is Q1, direct shear stress Q1 is equal to P by 2B plus D. That means if I write down clearly the C, only the weld part, this is a weld alone, so this width is B and this depth is D of the weld. Then I will have to find out the CG, centroid of this is CG. Then load is somewhere here, and from the CG this distance we call it as E, and from the extreme weld, this weld and this weld will be the critical weld. So this distance is nothing but my R max, and from the CG horizontal distance, this angle is the theta. So Q1 is the direct shear stress due to the vertical load, and another is a twisting shear stress due to twisting is nothing but a Q2 is equivalent to the P into E by IP into R max. R max is this, IP, this is a polar moment of inertia, and P is a load applied here P, and E is the eccentricity up to the centroid of the weld. So now I know the Q1 is the direct stress, Q2 is twisting stress due to the twist. So these extreme points get very critical. So the resultant stress at this point is the FE equal to square root of Q1 square plus Q2 square plus 2Q1 Q2 cos theta, Q1 Q2 cos theta, and theta is the angle between the extreme point between the horizontal CG line to the extreme point, and this resultant stress, this is the resultant stress must be less than or equal to Fu by root 3 gamma MW. Then you will mostly in this particular in plane bracket, load will not be given. The B, this width of the weld and depth of the weld will be given to you. You will be asked to find out the load, one kind of problem. Second kind of problem, that load will be given to you. You will be asked to find out the size of the weld, which is DE. So by equating this, you will be able to get the size of the weld. Thank you.